This is a continuation of problem session addressing exercises from chapter 5. Let me discuss for you exercise 9 on page 138. I will start with part A. The exercise has sub-questions A and B. A is relatively easy. So it is about show that z mod 2 of x factored over the polynomial x cubed plus x plus 1 is a field. Well, proof. Theorem 5.10 allows us to simplify everything. It suffices to check that the polynomial x cubed plus x plus 1 as a polynomial in z mod 2 of x is irreducible. That is because the polynomial has a relatively low degree of 3. Polynomial of degree 3, if reducible, must have a root. Indeed, the polynomial, if reducible, factors into two polynomials of positive degree, so 3 must be the sum of their degrees, and both positive one of these degrees must be 1 another 2. Otherwise, it cannot happen. Thus, if a factor is of degree 1, that factor has a root. All polynomials of degree 1 have their roots. Thus, we're left to check that their polynomial has no roots. We're left to check that x cubed plus x plus 1 has no roots in z mod 2 in the field. The field as a set is very simple. It has only two elements. This is a minimalistic example of a field. So as a set, Z2 contains only two elements, consists of two elements, 0 and 1. This is 0 is the class of 0 modulo 2, all even numbers. The class of 1 modulo 2, all odd numbers. And the obvious table of multiplication and addition, 0 plus 1 is 0 is 1, and 1 plus 1 is 0. Multiplication by 1 is 0, 1 times 1 is 1. That's how it looks like. Now I can write it as we typically write it, with brackets, and I will immediately drop these brackets, writing simply 0 and 1 for the classes of 0 and the class of 1, all even numbers, all odd numbers. Thus, what we need to check is that neither of them is a root. Oh, indeed, when we plug in 0, we get 0 cubed plus 0 plus 1, which is 0 plus 0 plus 1, 1. And when we plug in 1, we get 1 cubed, which is still 1, plus 1 plus 1. 1 plus 1 is 0. We are calculating in Z2. And 0 plus 1 is 1. So this is also 1. Not 0, not 0. So neither of them is a root. That's all. The polynomial has no roots because the field has no more elements to be suspected as a root. Thus, that's all by theorem 5.10. This is a field. Now, in 9b, we gotta, on same page, we gotta check that this field Z2 of x over modulo x cubed plus x plus 1 contains all three roots of the polynomial x cubed plus x plus 1. Now we think about the polynomial as polynomial with the coefficients in the field, or we may think about that as other way around. Every polynomial will be, just leave it alone. This polynomial has roots. Now, how did we do that? We know that by theorem 511. So first of all, by theorem 511, f contains a root of the polynomial so we can say that alpha be a root now. Let me do some arithmetic with this alpha. Let me show you some properties of alpha. Well, first of all, alpha is a root. Alpha cubed plus alpha plus 1 is 0. 0 in the field F, which actually coincides with the class of 0 as element of Z2. Now, about their coefficients, I'm thinking about their coefficients as elements of Z2. So in Z2, one plus 1 is 0, which implies that 1 is equal to negative 1. Thus, we can rewrite that as alpha cubed equals negative alpha 1, negative alpha, negative 1, but negative 1 is equal to 1. Negative alpha is negative 1 times alpha, and negative 1 is equal to 1. So I can write it as alpha plus 1. I can multiply that by alpha to get alpha to the 4, alpha squared plus alpha. I can do that again and multiply by alpha again, alpha to the 5, alpha cubed plus alpha squared. Alpha cubed is alpha plus 1. We already know that. So this is alpha squared plus alpha plus 1, because alpha cubed is alpha plus 1. I can multiply it again by alpha, alpha to the 6 is, multiply this by alpha, alpha cubed plus alpha plus alpha squared plus alpha, which is, what is that? This is alpha cubed plus alpha is negative alpha. So alpha cubed plus alpha cubed plus alpha is negative 1. Or I can write simply, instead of alpha cubed, let me write alpha plus 1. Plus alpha squared plus alpha. Now alpha plus alpha is equal to 1 plus 1 times alpha, and 1 plus 1 is 0. Alpha is an F. The 0 is 0 in Z2. So alpha plus alpha is 0 simply because negative alpha is equal alpha by the same token. And that is alpha squared plus 1. I think that is probably enough for our purposes. Now, I have a guess. Let us try alpha squared. Alpha squared. Is it a root? And the answer is yes. Look, we take x is it a root of our polynomial. Our polynomial is x cubed plus x plus 1. Plug in alpha squared, alpha to the 6, plus alpha squared plus 1. And let us use our arithmetic. Alpha to the 6 is alpha squared plus 1. One plus 1 is 0, and alpha squared plus alpha squared is 2 alpha squared. 2 is 0 in Z2, so it is also 0. The answer is yes. Alpha squared is a root. So, and obviously alpha squared is an element of F. Why? Because F, we know, is a field. Alpha is an element of this field. Field, being a ring anyway, has a closure axiom. So product of two elements of the field, alpha times alpha, is still in the field, must be there. So alpha squared is indeed another root. Point is, here, what we can find in this way yet another root, but we are a little bit confused. Maybe this alpha squared is equal to alpha. Maybe it is the same root. How do we know that this is a different root of that polynomial? Maybe it is a different way to write down same root. So it is actually better, and we have all hints here. We can go a step further and find that alpha to the 4 is another root. Or we can guess all roots in a more regular way. Take the polynomial and this polynomial, x cubed plus x plus 1, and divide the polynomial by x minus alpha, or trying to find other roots. We got a quadratic, we will somehow solve quadratic. Actually, to get, let me jump to the proof. Yes, I found another root, but I'm in trouble. That may be the same root written differently, and I don't see it's different. I can prove that, but that's gonna be lengthy. Let me just finish the proof. So I will, instead of going through guesses and checks. Make a big guess and check it. So I claim that x squared plus x plus 1 factors into x minus alpha, alpha is a root, x minus alpha squared, I suspect it is another root, and does not matter, different one or the same one, x minus alpha to the 4. At this moment, I don't know and don't really care whether it is alpha squared is equal to alpha or not, or alpha to the 4 is equal to one of them or not. I found a factorization into 3 factors, all of degree 1. Product of 2 factors, because they are monic polynomials, will give any 2 factors, will give us a polynomial of degree 2. That is definitely a non-trivial factorization, because the degrees are 1, 1, 1. That's it. If I support this claim, if I can justify it, I got that all roots are in the field F. All 3 roots, their polynomial cannot have more than 3 roots, and all 3 roots alpha, alpha squared, and alpha to the 4 are elements of the field. As soon as this is a field which contains alpha, it must contain alpha, and we know it is a field which contains alpha. It must contain alpha squared, it must contain alpha to the 4. Let us, so the claim, as soon as we justify this claim, we finish the exercise. We got all 3 roots, so this is going to be the answer. There are 3 roots, because this is factorization, it has no more roots than that. The polynomial cannot have more roots. These are all 3 polynomials of degree 1. We got all 3 roots of this polynomial as elements of F. So we're left with justifying this claim. To justify the claim, I multiply out so x minus alpha squared, x minus alpha to the 4. I multiply first the first 2, x squared minus alpha plus alpha squared, x plus alpha cubed times x minus alpha to the 4. Now I continue. X cubed plus now x squared, the coefficient of x squared comes from this multiplication and alpha to the 4. So the coefficients are negative alpha squared, negative alpha to the 4 x squared x. What are the coefficients of x? Alpha cube and alpha to the 4 times that. So we have plus, I believe. So again, minus, minus. So this is alpha to the 6, alpha to the 5, and alpha to the 3 x. Finally, what about constant term? Constant term is going to be alpha to the 7. All right, let me now use the arithmetic which I started with to simplify these expressions. So x cubed stands here. Now alpha to the 4 plus alpha squared plus alpha. I don't care much about the signs. 1 is equal to -1 here. So it doesn't matter all pluses or all minuses or any other combination. 1 is equal to -1 anyways in Z mod 2. So we have alpha to the 4, alpha squared plus alpha. Alpha to the 4 is alpha squared plus alpha itself. And this is a 0, because alpha squared plus alpha squared is a 0. 1 plus 1 is 0. This is alpha squared times 1 plus 1. By a similar token, alpha plus alpha is 0. 0 plus 0 is 0. Now, that sounds good. This coefficient is 0. What about this one? Alpha to the 6. Alpha to the 6 is alpha squared plus 2. Well, let me write it. Alpha to the 6 plus alpha to the 5 plus alpha cube. What is that? Oh, know what? I can do it in a different way. I can factor alpha cube out. Alpha cube plus alpha squared plus 1. Alpha cube plus alpha squared plus 1 is 0, because alpha is a root of our polynomial. Sorry, first of all, it is cube. Alpha is a root of this polynomial. We started with let alpha be a root of this polynomial. So this is 0. This is alpha cubed times 0. And this is 0. So this goes away, this goes away. What about the last one? You're there, right? The last one is, what is this? Alpha to the 7. Yes? Let us see what happens with alpha to the 7. We already have, we finished here with alpha to the 6. Alpha to the 6 is alpha squared plus 1. Let us add alpha to the 7. We need it. Alpha to the 7 is alpha cube plus alpha. alpha cube is alpha plus 1 here, plus alpha. Alpha plus 1 alpha is 0, and we are left with 1. This 1 may be considered as 1 in F or 1 in Z mod 2. This is the same thing. So we have alpha to the 7 equals 1. So the whole thing is, oh, sorry. I wanted to have, did I do everything correctly or not? At the moment, I possibly made a mistake. I made a mistake here. Sorry. Alpha cubed plus alpha squared plus 1 is not 0. This is a polynomial x cubed plus x, not x squared plus 1. So if I want to proceed, I got to write it as alpha cube. All right, let us do it this way. As I started to do, this is alpha cube plus 1. All right, let me use my arithmetic instead. Otherwise, I will go. It is better to write that alpha to the 6 is alpha squared plus 1. Alpha squared plus 1. This is alpha to the 6. We found it. Alpha to, again, alpha to the 6 is alpha squared plus 1. Correct. Plus alpha to the 5. Alpha to the 5 is calculated to be alpha squared plus alpha plus 1. Alpha squared plus alpha plus 1. And alpha cube. Alpha cube is calculated to be alpha plus 1. Now, let us see what happens. Alpha squared plus alpha squared is 2 alpha squared, which is 0. Alpha plus alpha is 2 alpha, which is 0. 2 is 0. But 1 plus 1 is 0, plus again 1 is 1. So this is x cubed plus x, what I calculated here as 1. So this 0 is the coefficient of x squared, while this 1 is the coefficient of x. And finally, I found that alpha to the 7 is 1. This is negative. Okay, negative does not matter. So minus, but I will immediately say that this is the same thing as negative 1 to write plus 1. Thus, we are done that this product is equal to our polynomial. We found factorization. Now alpha is a root. Then, as soon as alpha is a root, the polynomial factors. The polynomial factors into a product of 3 monic polynomials. It is with all three roots, alpha, alpha squared, and alpha to the 4, belong to the field as required. We're done with this problem. Please pay attention. I did not really calculate anything about the root. I don't know the root and I don't know other roots. I don't know whether they are all three equal or all three different or whatever happens there. What I know that if alpha is a root, then this polynomial factors this way. Therefore, because it can alpha, alpha squared, and alpha to the 4 are all three roots. The polynomial cannot have more than 3 roots of the polynomial. All three roots of the polynomial are alpha, alpha squared, and alpha to the 4. As soon as alpha is an element of the field, so are alpha squared and alpha to the 4 by the closure axiom. So I did not need any calculations related to how this root can be written as an element of the field. Elements of this field, because this is degree 3 polynomials, are classes of degree 2, 1, and 0 polynomials. This alpha, alpha squared, alpha to the 4 are among them, but it will be much lengthier and more annoying way to really write alpha and others as these polynomials. Alpha is not difficult, it is the class of x. But others as classes of something, this is going to be the class of x squared, of course, and there is no class of x to the 4, you have to reduce it somehow. I didn't do that. I just did not use any explicit description of this field F as set of equivalence classes of polynomials with correspondingly defined operations. I did it without all that, just supported this factorization. And there are some hints how to find the factorization. Divide this polynomial by x minus alpha and find roots of the quadratic. All not so difficult. Or just guess, as I did, that alpha squared is a root. Probably alpha to the 4, alpha to the 3 is not, but alpha to the 4 is. So that is a solution which does not require explicit representation of roots as equivalence classes of polynomials. I work inside a field. What I need to know, it is a field. But that was guaranteed by theorem 5.10. I need to know that this field has a root. That was guaranteed by theorem 5.11. All right. So let me do yet another problem from this problem set, or it is also going to be a lengthy, so let me start with a separate page, and that is 10 on the same page, 134. Oh, no, it's not 134, it is, sorry, let me see, did I do right, correct, 138, yes. 10 on page 138. The problem is so that the two fields q of x factored by modulo a polynomial x squared minus 2 and q of x modulo the polynomial x squared minus 3 are not isomorphic. So here is the solution. We need to show that two fields are not isomorphic. For that, we will make use of an explicit description of these fields, which we already did, at least for this field, we did it. So let us make use of this description. So if there is, so this field, we can go both ways, but let me try to go from this one to this one. So the field q of x cubed minus x squared. This field, this is a field because x squared minus 3 is an irreducible polynomial over rationals. There is no rational whose square is 3. And the polynomial of degree 2 has no roots, therefore irreducible. This field contains a root of this polynomial. Which is a polynomial, and the field contains a root. Thus, there is an element of this field, call it U, such that U squared is 3, a root. Of the polynomial. U squared minus 3 is 0, U squared is 3. If there was an isomorphism say, call it phi, from this field x squared minus 3 to this field, Then 1, which is the class of the polynomial 1 of degree 0, must map to 1. 3 or 2 will map to 2, 3 will map to 3. And u will map to something which we call phi of u. Now, phi is an isomorphism, homomorphism at least. So what will happen with u squared? So phi of u squared must be equal to phi of u squared. At the same time, u squared is 3. But u squared is 3. So phi of u squared, phi of 3, 3 must map to 3 because 1 maps to 1, and 1 plus 1, 2 maps to 2 because 2 is 1 plus 1. So I will show you for any for any isomorphism. 1 maps to 1. 1 is a special element, neutral element for multiplication. After that, phi of 1 plus 1 must be isomorphism, or just homomorphism, phi of 1 plus phi of 1, which is 1 plus 1. This is 2. So phi of 2 is 2. Phi of 3, phi of 2 plus 1, phi of 2 plus phi of 1. Phi is a homomorphism, isomorphism, but in the first place, homomorphism respects addition. But phi of 2 we know is 2, phi of 1 we know is 1, so that must be 2 plus 1, which is 3. So phi of 3 is 3. Phi of u squared must be phi of u squared because this is homomorphism. I can write it for you in more details. It is phi of u times u, which homomorphism must be phi of u times phi of u, and that is phi of u squared. So now, if there was a homomorphism, then by this calculation, then the field q of x squared minus 2, modulo x squared minus 2, must contain, or would contain, an element call it somehow v, which is phi of u, such that v squared is 3. phi of u squared is, this is same phi of u squared, which is phi of u taking squared, and this is 3. So phi of u squared is 3, so there must be such an element. To prove that the two fields are not isomorphic, it now suffices to prove that the field, that no element V in this field has the property V squared equals 3. Now, let me recall from an exercise which I discussed in details. So now recall from exercise 6 on page 134. This field as a set as the set of all ax plus b, well, if one classes of these polynomials of degree 1, a, b are rationals, and we know how to multiply two of them, x plus b multiplied by cx plus d as bc plus adx plus bg plus 2ac. Where I discussed that in as much details as I can in one of the previous fragments. Now I want to show that no square is 3, so I multiply. So if such an element exists, such a V exists, there should be ax plus b cx plus d equals the class of 3 is 3, and the class of 3 is same thing in this field. All right? That means, after all, that I use this formula, BC plus AD x plus BG plus 2AC is the class of 3, meaning these are two linear polynomials we discussed. Either to be in the same class, they must be the same. Two different polynomials like that, two different expressions like ax plus b are in different classes modulo x squared minus 2. So the two polynomials must be the same, this one and this one. What we get from that is that, oh, sorry, no, sorry. Yeah, yes, they should be the same, but it should be multiplication by the same polynomial. This is the point. I'm sorry. Ax plus b. Let me write it here. If there was u ax plus b such that u squared, v, I called it v, such that v squared is 3, then we would have and now instead of BC plus AD, what should I write? This is 2AB. This one and that one. So it is 2AB times x. And this is not BG but B squared and not plus 2AC. But plus 2A squared. A and C are the same, B and D are the same. So this should be B squared plus 2 well, just a moment, again, yes, BG, B squared plus 2AC, this one times this one, A squared. Oh, great. So these two polynomials must be the same. Thus, must be the same, the class must coincide, but both are expressions as ax plus b, and we discussed in this problem that two such expressions, two such polynomials belong to different classes if they are different, because the difference cannot be divisible by x squared minus 2 unless the difference is 0. x squared minus 2 has degree 2, the difference between two different expressions of this sort ax plus b may have degree only 1 or 0. Polynomial of degree 1 or 0 cannot be divisible by x squared minus 2, so all these are all different expressions are in different classes. So now we have two expressions. They must be in the same class, meaning that is what is written, meaning the expressions must be the same. Thus, we can write that, first of all, 2ab must be 0, and secondly, b squared plus 2a squared must be 3. 2ab is 0 when either a or b is 0. These, after all, now are, sorry, just a moment. I will try to fix that. I fixed it. So 2ab is 0 implies either a or b is 0. This is already an identity for just rational numbers a and b, and this 0 is just 0 as a rational number. We compare these expressions already as expressions themselves, so the equality must be indeed equality, not modulo something. We got rid of divisible by x squared minus 2 in these cases means equal. So either we must have we thus must have a equals 0 or b equals 0. That is all right, this is still possible. But the second equation, in the case a equals 0, the second equation becomes b squared equals 3. In the case b equals 0, the second equation becomes 2a, so b equals 0, and the second equation becomes 2a squared equals 3. Now, there exists no rational number whose square is three, and no rational number whose square is 3/2. We probably know that, or can easily prove that using the fundamental theorem of arithmetic. A square of rational number has to have this rational number as integer over integer. We write the decomposition into primes, square, and say that this is not 3 alone. All primes will have positive or negative but even powers in a square. Same here with 3 over 2. So that can be easily proved using the fundamental theorem of arithmetic. Which we already proved. So this is a rational number, so it's integer over integer. Both integers are going to be uniquely decomposed into a product of primes. Take a square and see what happens. No, it is not one prime alone. No, it is not one prime over another prime. That's all. We are done. So thus that cannot happen for no AB. Thus no element V in this field has the property V squared equals 3. Therefore, the isomorphism we were speaking about cannot exist. This isomorphism implies the existence of such element. This is the image of certain element U in this field. And the isomorphism phi cannot exist. For that reason. So, we did it. The two fields are not isomorphic. The idea was we found some element here which cannot exist. One may argue from the very beginning, what did we do? In this field, the equation x squared minus 3, the polynomial x squared minus 3 has a root. What we proved, this same polynomial does not have a root in this field. That alone would not be the argument, would not be a completed argument. So I tried to explain why this observation that a polynomial has a root here but does not have a root here implies that two fields are not isomorphic. I tried to spell it out why, indeed, that implies the non-existence of an isomorphism. So isomorphism tells you that the fields are the same up to the labeling elements. If they are the same polynomial must have a root. But there are some difficulties with this kind of hand waving. What does it mean, same polynomial? Maybe this polynomial becomes the same as this polynomial. Why not? So I was trying to make this argument precise, and I hope precise and transparent for you, that this property indeed boils down to non-existence of a root of this polynomial, non-existence of such an element whose square is 3. 3 can be considered as an element of Q, or a class of 3 as an element of this field, 3 in brackets. 3 must map to this 3, so this is the same 3, not this 2. And now how to prove that there is no such element in this field? Now we simply use a description of this field. And how do we multiply elements in this field? Now we multiply an element, any element of this one, because this is a full description of this field. All elements with distinct pairs, ordered pairs of A, B are different. We multiply element by itself, and we find what does it mean. This equation is satisfied. This is the same element now, square of this and 3. Everything boils down to non-existence of a pair of integers, not integers, rational numbers, which satisfy that. That means exactly these two equations. Now we are solving two equations for rationals A and B, and find why these two equations cannot have no rational solutions. That's a detailed proof of this non-isomorphism between two fields. So they are really substantially different. Although, in a sense, quite similar. For me, rather quite different than quite similar. All right. Thank you for listening.